Welcome to the lab demonstration video for the copper-amine synthesis and spectrophotometric analysis lab, presented by Erin McVeigh, Marianne Mowdy, Cecilia Nguyen, Emily Hatcher, Braxton Miller, and Jamiah Williams. The students first tare the balance and use it to obtain a precise amount of copper sulfate pentahydrate, 0.125 grams to be exact. The solute is dissolved in a small amount of water, and concentrated aqueous ammonia is added to the solution under the fume hood. Finally, the solution is diluted up to the mark with water in a 25 milliliter volumetric flask, capped and inverted to mix. The students' observations of the stock solution are noted in their lab notebooks. 3 serial dilutions are prepared using the same method, beginning with the stock solution as the solute, and 2 solutions are prepared from an unknown solution. The students transfer the stock solution, 3 dilutions, and a water blank to cuvettes, ensuring that the meniscus of each solution rests on the line of the cuvette and not above it. After calculating the molarities for the dilutions from the known solution, the students make the trek to the spectrophotometry room to find the relationship between the concentration and the absorbance in the solutions. The water cuvette acts as a blank so that the spectrophotometer may be zeroed out so that it does not measure the light absorbed by interfering substances other than the intended substance. Since a dilution is being measured, we must account for the absorbance of water and the cuvette. Failing to zero out the machine would result in false reports of higher absorbance values that are inaccurate for the copper-amine in the solution. The students wipe the outside of the cuvettes with a Kim wipe, placing the clean sides of the cuvettes facing the sides of the machine from which light will be emitted, and close the lid of the spectrophotometer. The spectrophotometer scans across all wavelengths in a certain range to determine the most useful wavelength or the best peak for determining the absorbance of all of our solutions. Scanning across all wavelengths allows for the determination of the lambda max, which is the wavelength at which the solution has the highest molar absorptivity. The lambda max gives the maximum likely value for the wavelength with the greatest absorbance value, and it gives an accurate wavelength of highest absorption to which other substances can be compared. After recording the values from the scan in their notebooks, the students manipulate the Beer-Lambert Law to determine the concentration value of the unknown solutions. The Beer-Lambert Law demonstrates the linear relationship between concentration and absorbance. The Beer-Lambert Law states that absorbance is equal to the molar absorption coefficient multiplied by the molar concentration multiplied by the distance traveled by the light through the sample. The absorbance is determined using the spectrophotometer. The molarity is determined using the equation M1V1 equals M2V2, beginning with a solution of known molarity, and the distance is simply the length of the cuvette. After these calculations are completed, the students prepare a graph of their findings. And finally, we would all like to wish our wonderful TA Maizi a very happy birthday. Thanks for watching, and we'll see you next time.